Okay, mathematics often involves looking at the same thing in different ways. So we're going to revisit modular arithmetic in light of what we've learned about equivalence classes. Okay? As a review, remember that we define modular equivalence in the following way. Now look, this is a relation. This is a relation between integers. A is equivalent to b, mod n, if and only if a and b have the same remainder when divided by n. Here's another alternative definition, which is often more useful. A is equivalent to b mod n if and only if a minus b is an integer multiple times n. All right, this should be definition 40 here. All right, so we want to prove that, in fact, this is an equivalence relation. You want to show that this relation is reflexive, symmetric, and transitive. So now we can carry over some of the things we've been learning about equivalence classes. Now let's look at one specific example, the integers mod 3. Okay, so what are the equivalence classes in this case? Now we know that when we divide an integer by 3, the remainder is either 0, 1, or 2. That means every integer is equivalent either to 0, 1, or 2. So that gives us our 3 equivalence classes. We can write down these equivalence classes. They're infinite sets. If you write these on a number line, the first class is going to be 0 in every third integer. The second equivalence class has 1 in every third integer. And the third equivalence class has 2 and every third integer. Okay. So in fact, every integer is in one of these equivalence classes. One and only one and exactly one. Right. So we're going to define a new symbol. We have the equivalence classes, the equivalence class of 0, equivalence class of 1, equivalence class of 2, 3 equivalence classes, and we're going to call these another representation of the integers mod 3. Right. Now before we just called the integers mod 3 0, 1, and 2, but now we're going to reconceptualize these elements and call them and identify them with 3 equivalence classes. 2 different notations. Here's one way of drawing the 3 equivalence classes. Here's another way with a bar over it. That means the equivalence class. Now let's define some arithmetic operations on these equivalence classes. Now we have these equivalence classes are mathematical objects, and we can define operations on them. So here's a definition. Now be careful. This is actually plus used in a new way. Never before have we used plus between equivalence classes. Here we're saying the addition of 2 equivalence classes is the equivalence class that contains the addition of the 2 elements. This is ordinary plus. This is a new plus. Same with a minus here. This is a new minus. This is ordinary minus. Okay. Say, for instance, if I want the equivalence class of 5 plus the equivalence class of 7. Well, that's the equivalence class of 5 plus 7, or 12. So it turns out the equivalence class of 5 is 2. The equivalence class of 7 is what? 7 is 1. And the equivalence class of 5 plus 7 is 0. Okay, so emphasize again that these plus, minus, and dot over here, these are new meanings for these symbols. Okay, so be careful when you're applying this algebra. Okay, so here's some more examples of how you do the arithmetic. So here's a rule for computing, and you can make a Cayley table that does the operation, and this is just the same Cayley table that we generated before. It's just that you're going through different concepts to arrive at this table. All right, now what we did for mod 3, we could do for mod n. We can get equivalence classes with respect to that equivalence relation mod n. And these equivalence classes we can identify with the integers modulo n. There will be n equivalence classes. Here we define addition, subtraction, multiplication the same way. This really should be dot. We were using dot for multiplication. Okay. All right, so here we have the equivalence class listed. Okay, and this should be a dot here too, because we're talking about multiplication in Z12. And when here we're talking about Z12, we're talking about equivalence classes. Okay. So this X represents an equivalence class. It's not a number, it's an equivalence class. All right, now let's backtrack a little bit. When we defined the sum of two equivalence classes, we neglected to check a very important point. So let me show that point here. Now, the equivalence class of A is a set that contains A. The equivalence class of B is a set that contains B. These could, in fact, be the same class, but I don't need to worry about that for purposes of this argument. Now, the equivalence class of A plus B, the equivalence class of A plus equivalence class of B was defined as the equivalence class that contains A plus B. Now, there's a problem here. Suppose I chose A prime here and a B prime here. How do I know that I'd get the same definition if I use A prime and B prime instead of A and B? How do I know that I'll end up here, A prime plus B prime? In other words, how do I know I really have a consistent definition of the sum of equivalence classes? Well, that's an important point. Okay. Actually, here, down here, this is the point here. Now, this is a mistake here. That should be B1 and B2. Okay. So instead of A and A prime, this is making the same point with A1 and A2. I have A1 and A2 here, and I have B1 and B2 here. And in order for addition to be consistent, it must be the case that A1 plus B1 and A2 plus B2 are in the same equivalence class. Otherwise, the definition of addition is not consistent. So we have to prove that for addition, subtraction, and multiplication. And here's an exercise for you to verify that. Now, this is a big deal because there are some operations in which this doesn't hold. Right, there shouldn't be a z there. And here's an example. Exponentiation doesn't actually work. And absolute value doesn't work either. Okay, so you can do some of these exercises. This should be z12, sorry, that's a mistake there also. Okay. All right. All right, now last section, we've been talking about equivalence classes derived from equivalence relations. And actually, we've gotten equivalence classes from equivalence relations. You can actually go the other way as well. If you have a set of classes that divide up a set, you can use that to define an equivalence relation. Okay? When we classify elements of a set, we're breaking the set up into subsets. So here's the picture. This is a picture of what is called a partition. You have the whole set A, and it's divided into disjoint subsets that make up the entire set. Okay? So we call this a partition. A partition of a set A is a collection of non-empty subsets such that every element of A is in exactly one of the subsets. That's another way of saying the union of these subsets is A, and there's no intersection between any two of these sets. Okay. All right, now, if we do take any equivalence relation, and we take all the equivalence classes generated by that equivalence relation, that will form a partition. In other words, if we draw the equivalence classes diagrammatically, we'll always get a picture something like this. Okay, you notice that when if I took all the integers, and I take the equivalence class of 0, equivalence class of 1, and equivalence class of 2, those three sets are disjoint, and they comprise the entire integers. Okay. Now this proposition says we go the other way. If I do have a partition, I can define a relation on the set A by saying two numbers are equivalent if and only if there's an equivalence class such that they're both in the same equivalence class. Okay? So to go back up to this picture, I'm saying that two elements are equivalent if and only if they're both in the same equivalence class. So everything in here is equivalent. So I could start with this partition and generate an equivalence relation. So that's what this is saying. Okay, so where are we? Okay. And we have various examples here. Okay, and that's it for this chapter. Lots of examples to work. Should give you a lot of familiarity with the concepts.